This is a walkthrough of Problem 2 on Exam 2 of Module 5 in the book Problem Solving Guide for Mechanics and Thermodynamics. 2 kilogram block at rest on a 36.9 degree incline. Block is attached to a rope, to a spring via a rope. There's the spring. The spring has a stiffness of 100 newtons every meter. It's unstretched. When the block is released, it slides down the plane. The spring gets stretched. The spring stops it 20 centimeters down the incline. The block goes 20 centimeters down the incline and it stops. What is the coefficient of kinetic friction between the incline and the block? That's all we have to do. What's mu sub kinetic for these two surfaces? The total work done by all the forces is 0. The block starts at rest, slides down 20 centimeters, and stops. Starts at rest, ends at rest. Total work done is 0. We can get the work done by the gravitational force, mg delta y. The block goes 20 centimeters down the plane, but we need the distance it moves in the direction of the gravitational force. How far did it go down? So let's do some trig. There's the 20 centimeters. The block went down the plane. We need to know the height. So that's 20 centimeters sine 36.9 degrees, which is 12 centimeters. So now we can get the work done by gravity. It's positive. The block's going down. The gravitational force is down. 2 kilograms times 10 newtons every kilogram times 0.12 meters. That's plus 2.4 joules. The spring is exerting a force opposite the motion, so it does negative work. The work done by the cord, minus 1/2 kx squared. There's the spring constant given. The spring gets stretched 20 centimeters when the block goes 20 centimeters down the plane. So that's 0.2 meters, and we get minus 2 joules for the work done by the spring. Gravity made a deposit of 2.4 joules into the kinetic energy of the block. The cord made a withdrawal of 2 joules. The frictional force must have made a withdrawal of 0.4 joules because the balance in the kinetic energy account of the block is 0. So the cord, spring, took away 2 joules. Friction took away 0.4 joules. Gravity made a deposit of 2.4 joules. The block is at rest. So now we know the work done by friction is 0.4. Okay, it's negative, but we don't pay attention to that negative sign. We know what's going on, right? Friction's not speeding up the block in this situation, right? The work done by friction is the frictional force times the distance over which the frictional force acted. The work is the force times the distance. The force is constant. It's the frictional force. We know the work is 0.4 joules. The distance is 0.2 meters. We divide both sides by 0.2, and we get the frictional force is 2 newtons. We need the coefficient of friction. To get that, we need the normal force. We got to do force diagram. Gravity, normal force, tension, and that tension varies, of course. As the spring gets stretched, that grows. But we don't care about that direction. We just care about the y direction. No acceleration in the y direction if we draw our axes like this. A lot of stuff's going on in the x direction. The motion's complicated. In the y direction, there's no acceleration. So we need to get the normal force. The force equation in the y direction is Fn is pure y, straight up. And in the negative y direction, we have mg cosine 36.9. Those forces balance. The acceleration in the y direction is 0. And we can calculate. We have all those numbers, and we get 16 newtons. So the normal force on the mass is 16 newtons. The frictional force is 2 newtons. The frictional force is mu kinetic times the normal force. The normal force is 16 newtons. We can solve for mu kinetic right here by dividing both sides by 16 newtons. Mu kinetic is 2 newtons over 16 newtons, which is 1/8. Dimensionless, of course, which is 0.125. If you like decimals, 1/8 is fine. That's a nice mu kinetic. I'm happy with that. Looks good to me. That's problem 2.